Alright guys, so for work, the big thing you need to know is that the work is going to be the integral of our force times our displacement, some small dx. That's really it. It's our force, and our force is generally going to be a function of some sort of distance. So we're taking force times distance, so we're going to do each small change in distance and add up our total number of changes, which is where our integral comes into play. So Hooke's law for springs is our force is some sort of constant times some sort of distance. So to find our work, it's going to be the integral of k d d d. A lot of these end up with dd because our distance is going to be in terms of d, which is kind of a little bit of a strange. So if you want to make it kx, we end up with the integral of our force, which is kx dx. Gravitation, it's the same thing. You're just integrating k, one mass of one thing times the mass of another thing, all over some sort of displacement squared, dd, and you're going to toss in some bounds. Coulomb's law, which is the force between two charges, such as one electron and another electron, or an electron and a proton, would be k times whatever the two charges are, divided by the square of their distance. These look pretty darn similar, don't they? So our integral is going to be very similar. Now generally k times m1 and m2 is just one constant. So in a problem like this, you can replace it with some big K, which you can figure out on your own, 1 over d squared dd. So constant can come out front, and you can actually figure this out just in general. It's our constant, and then you use your power rule. Bring out a negative, so negative k d to the negative 1 plus c. But generally we just want to think of it as we want to take the integral of f dx. So let's see if we can get a problem here. Alright, so Kyle's trying to do the circus game where you get tied to a spring and try to run to the other end of the attraction. How much work would it take to run 20 feet with a constant of proportionality of 45? So we have a spring basically, and so you've got our force equals k times x. And the constant proportionality is 45. That's our k value. So our force equals 45 times x. Now we want to know how much work, not how much force. So if it was how much force, then you could just plug in 20 directly. But we want to integrate, bring out the 45, x dx, and we want to run 20 feet. So we're going to go from 0 to 20. And you get a number, and it's going to end up being in feet times, well, you don't know in the end because this constant would tell us if we're in terms of pounds, so it's foot-pounds or whatever. So you got to figure out what your constant is in terms of, but dx would be, in this case, feet. So feet times, I don't know, let's say pounds. But it wasn't really written in the problem. So that's really the process here. So let's try one more here. Chris wants to be an astronaut. Remember, you can be anything. And we know that him and his shuttle weigh 300 tons on Earth. How much work does it take to send them up 900 miles? So we have to work with gravitation in this problem. So our force is k m1 m2 over d squared. All right, so this one isn't quite as straightforward as the last one, or at least it doesn't look like that at first. I don't know what the mass of the Earth is. I don't know what the mass of the shuttle is, and I don't know what k is. But I do know that a shuttle weighs 300 tons on the Earth. This is a unit of force. So 300 tons equals, well, this is some sort of constant on the top over our distance squared. Well, on the surface of the Earth, we're going to use the radius of the Earth to be the distance. So Earth's radius, you got to think of, you're sitting out here on Earth's radius ready to blast off into space. When you talk about the gravitational force that you're you're feeling some gravitational force because you are some distance from the center of the Earth. If you were at the center of the Earth, your distance would be 0, and you would feel, well, if you look at the formula, you're dividing by 0 at some point, an infinite number of force. That's a little bit of a problem as far as that goes. But you really can't get 0 distance from something. You're always some ways away. But as your distance gets bigger, your force gets smaller because you're dividing by, so as your distance gets larger by the square of it, you're dividing by a bigger and bigger number, which makes it, your force end up going smaller. But anyway, when we're on the surface of the Earth, we are 4,000 miles from your actual value. So we can solve for K, multiply through over here by 4,000, and then that's a big number. I would store it into K. So when we want to find out how much work does it take to send 900 miles, we're going to go from 4,000 miles, not from 0, because we start at 4,000 miles, to, well, I really don't want to go 900 miles because that's down a whole bunch. We're really going from 4,000 to 4,900. We can pull out the K, which we just found, 1 over d squared dd. And now we're going to use our calculator to figure out what this value is. 3 decimal places. And in this case, the units would be, well, force, tons, times dd, which is in terms of miles. So ton miles.